Okay, that's the today is the numerical method. I will continue the last hour. Uh, Last hour I introduced the Jacobi's method, also the generalized Jacobi's method. The Jacobi's method can be used to solve the standard eigenvalue problem, and the generalized Jacobi's method can be used to solve the general eigenvalue problems. And last time we say for the general eigenvalue problem, okay, we can set the rotation matrix. However, for the rotation matrix, we need to use two variables. And let's say we can use the two variables alpha and gamma. And when we iterate the solution procedure, in each procedure we can make both Aij elements and the Bij elements. We can make both the ith row and the jth column elements in these two matrices. We can make them equal to zeros. Okay, so after several iterations, we can get the A and B, both A and B, they will approach to the diagonal element, diagonal matrix. Okay, so since all the off-diagonal elements, we can make them smaller and smaller, and after many iterations, the matrix will close to the diagonal matrix. Okay, so okay, this is the operations here. Also, the operations approach to the diagonal matrix. And why in the when we calculate the if we like to get the eigenvector matrix gamma, if we put all the eigenvectors in a matrix, and this matrix can be said that it is the gamma matrix, and we can prove the will be a diagonal matrix. Okay, since all the eigenvectors, they are orthogonal to the with respect to the A matrix, and it is also true when we put the center matrix. If we change the center matrix from the A to the B matrix, it is also okay. But usually when we multiply the T1 until all the Tn, we will make a modification for the matrix. You can say if we multiply all the rotation matrices together, you can get a set of the eigenvectors. However, usually we will change the values of this one. Okay, the reason why we like to change the values. First, remember the if we know the lambda I and the xi, which are an eigenpair, so means it can fulfill these equations. If we multiply by the ith eigenvector, it will be equal to the lambda I times b times xi. If this one is true, then we can prove the okay. So if we like to get the lambda I, we can always use the formula. Okay, we can always use this formula to calculate the lambda I, no matter which eigenvalue and which eigenvector. Okay, so this one we can always use this formula to get the lambda I. Also remember, if we multiply any variable, let's say beta times xi is also the eigenvector. Okay, if we know the xi is one of the eigenvector, then we can prove we can multiply any constant. We can multiply any constant to the eigenvector, and the result still an eigenvector. And this one can be very easy to prove. If we replace the beta xi to this formula, you will find the formula still, which is also this equation still exists. So we can prove we can multiply any constant to an eigenvector, and the result is still the eigenvector. So we can multiply any constant to the eigenvector, and it doesn't matter which constant we need to multiply. Okay, so sometimes we like to do a procedure which is called the normalization procedure. Okay, since we can multiply any constant, to the eigenvector, and the result still an eigenvector. So we can do the normalizations. The normalization procedure, since we like to get the xi, which is normal to the matrix. Okay, so we like to get the results. Which is equal to 1. We like to get the eigenvector which is normalized with respect to the B matrix. So it means that's the result we like to get. Okay, so if we got the xi, and how can we do the normalization to this one? We can calculate the xi, which is, if we know x bar is the eigenvector, then we can calculate the xi, which is the okay. We can divide the original xi bar by this value. So the beta is okay. If we multiply this constant to the original xi bar vector, then we can get the xi vector. Now the xi vector, which is normalized, eigenvector. Okay, the normalizations, we like to make it normalized to the B matrix. Okay, so then we can go back to the generalized Jacobi's method. Since if we can get the A bar, if we know the A bar is the, after we make a series of the iterations, and we know the A bar approach to the diagonal matrix right now. Also the B bar. The B bar also we need to do the same procedures to the B matrix. And right now the A bar, both A bar and the B bar matrix, they approach to the diagonal matrix. Okay, and also we know in these solution procedures, the eigenvalues will not be changed. We say if we do the similar transformation, the eigenvalues will not be changed. Okay, so okay, in this we know the eigenvalues will not be changed, and also both A bar and the B bar, they are the diagonal matrix. And then we can prove the 1, 0, 0, 0 is the eigenvector. A bar and the B bar. And the lambda is equal to A bar 1, 1. And also lambda 2 is equal to. That's for the 0, 1. That's the eigenvalue we can get this. If we use the 0, 1, this 1. Okay. So we know the 1, 0, 0, which is an eigenvector. And how do we do the normalization? If we do the normalization, so we know the 1, 0, 0, 0 is the eigenvector. For A bar, B bar. And also we know the lambda 1 is equal to A bar 1, 1, and if we like to do the normalize the x1. Okay, then we need to calculate the which is equal to the B bar 1, 1, which is equal to the B bar 1, 1. And the one is the normalized eigenvector. Also, you can prove the normalized eigenvector. Okay, so that's the eigenvector for the A bar and the B bar. And if we like to solve the eigenvector for the original matrix, the x1. And then also we will multiply the okay, so if we like to get the gamma matrix, if we like to get all the eigenvectors, not only the T1, T2 until the Tn, we can multiply them together. Also, we can multiply a diagonal matrix which is equal to this one. And the results eigenvector, they are the normalized eigenvector. Okay. Okay, so I will finish the generalized Jacobi's method right now, and I'm going to the next method, which we can use to solve the eigenvalue problems. And let's okay. That's the eigenvalue problems. We have the A matrix and the B matrix, and we like to solve the eigenvalue lambda and the corresponding eigenvector x. And also we can say if we change the form. If we move the right hand side to the left hand side, the eigenvalue Then we know all the eigenvalue lambda. If we replace the lambda into these matrix operations, then if we calculate the determinant of this A minus lambda B matrix, we know the determinant must be equal to 0. Since the x is not okay. Since we like to get the eigenvector, but also we know the eigenvector is not the trivial solution. So the elements in the x vector should not be all equal to zeros. Okay, that's not the matrix we like to get. Okay, so we know these equations must be equal to 0. And if we really calculate the determinant, which can give you the characteristic equation. The characteristic equation. Okay, so the characteristic equations, which is the nth degree polynomial function of lambda. Okay, if we calculate A minus lambda B, the determinant of this matrix, we will find the since we know all the elements in the matrix A, also we know all the elements in the matrix B, so we can calculate the determinant of this matrix, and you will find the results should be nth degree polynomial function of the lambda, and these nth degree polynomial functions we called it is the characteristic equation for the eigenvalue problems. So the other way to solve the eigenvalues is we can try to find the root of the characteristic equations. Okay, so we can try to solve the roots of the characteristic equations, and especially for the small dimensional problems, since if the number of the n is not a very large number, we can try to solve the characteristic equations directly, and in this case we can get the eigenvalues first. Okay, so for example, if we have 5, 3, 2, 1, 1, 1, 1, 0, 0. Okay, it is a three-dimensional eigenvalue problem. The dimension for the matrix, which is only 3 by 3. Then we can try to solve the characteristic equations of these problems. So what is the determinant of the So this one is the determinant of the A minus lambda B matrix, which is the in this matrix, which is the A minus lambda B, and the determinant of this matrix is the which is the characteristic equations. Then we can get okay. So then this this equation is the characteristic equations. We can try for this equation, which is the in this for this characteristic equation, it is third degree polynomial functions of the lambda. And if we can solve these characteristic equations to find the roots of these equations, then we can get the eigenvalue. Then we can get the eigenvalue. And a typical example for these problems first, we can put the Cauchy's trace. Okay, for this formula, it is the Cauchy's theory, and this matrix, sometimes it is called the Cauchy's trace matrix, and the nx, ny, and the nz, they are the unit normal vector. They are the unit normal vector of an inclined surface. And the Tx, Ty, and the Tz, they are the surface traction. They are the elements of the surface traction of this inclined surface. So we can change it. We can always change the normal vector of the inclined of any inclined surface, and to find the surface traction of this inclined surface. And also we know for any stress conditions, we can find three principal directions. In the principal directions, we have only the normal stress, and the shear stress on along the surface of the principal directions, the shear stress, they are always equal to zeros. Okay, so if we put the formula in this one, for Okay, since we know along the principal directions, in this surface there is only the principal trace. So the surface stretching should be parallel to the normal vector. It is the definition for the principal trace, also the principal directions. Okay, I think I will take a break here, and I will continue it in the next hour.